All right, so here we go for today, starting chapter 5. All right, and again, we're going to talk specifically in chapter 5 about the different properties of triangles. All right, and today's property is going to be the perpendicular bisectors. All right, now let's recall what a perpendicular bisector is. A perpendicular bisector is a line, segment, or ray that is perpendicular to the given segment and passes through its midpoint. All right, so let's just review that real quick just to make a quick little demonstration. If I say that is a segment, then I will try to draw the perpendicular bisector. All right, so if I draw the perpendicular bisector, now notice I'm going to do something like this. So because that is the perpendicular bisector, what is true? If I call this A, B, C, I call this D, and I call this E. Somebody tell me what's true. Morty.
That AB is congruent to BC.
That is correct. AB is congruent to BC. This is congruent to this. All right? And what else?
AC is perpendicular to BD.
That is correct. That's all that means, guys. Super easy. All right? Now, again, what I would like to demonstrate now is I'm going to draw DA. And then I'm going to draw DC. And what appears to be true? Tell me. Yes, there are two right triangles. Two right triangles are constructed. Somebody else tell me what is true. What do you think?
AD is equal to DC.
Yes, very smart. AD is congruent to DC. How do I know that, though? That is correct. But before you say CPC, yay, very smart. All right, I'm proud of you for that. This right here is congruent to itself. Come on now, this is the kind of stuff that I think is just so simple that I tell kids every year, there's no way to memorize everything. All right, so I really and truly don't have things memorized. Every time I do this every year, I just realize how simple it is. All right, because all you have to do is draw it and then you can make your own conclusions. Does everybody see that? All right, so a triangle ABD and triangle CBD are congruent by side angle side, and then he said it perfectly. AD is congruent to CD by CPCTC. All right, so let's draw now EC, bless you, and AE. Now, someone wants to tell me what's true about that. Go ahead. AE, again, is congruent to EC. What do you think? Exactly correct. Exactly. All right. So what happens if I put a new point here and call this F? What's true about that point? If I draw from here to here, and I draw from here to here, what's true? Tell me again. So what's always going to be true when I put a point on the perpendicular bisector? Tell me. Yeah. So what are we want to say now? Summarize it for me. Someone else summarize better. Tell me. Yeah, it always makes two congruent triangles. That's exactly correct. But now I want somebody to specifically say something about any point that is on the perpendicular bisector. It is always what? Equidistant from the endpoints. That's exactly correct. Now again, I just think there's no reason to memorize that. I just think anytime you would draw that, you could obviously see that's true. So everybody agree with me on that? All right. So if you are on the perpendicular bisector, that means you are equidistant from the endpoints. All right. Is everybody good with that? All right. Now let's look and see what it says. The perpendicular bisector theorem. Again, it's called a theorem because we just did what? We just proved it. All right, we just proved it. So it says, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segments. Does everybody agree with that? And does everybody agree we just proved that? But did I write the proof? No, but it was easy to write the proof. All right? Hopefully feel good about that. All right? So now, the converse of the perpendicular bisector theorem. If a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. All right, which is obviously true. All right, now something that's not so true, or not so obvious, I should say. The circumcenter. All right, I'm just gonna, in the past I've done constructions with my geometry class, but I stopped doing the constructions because just out of time. All right, I want to spend more time on the algebra parts. All right, so my construction unit has, I haven't been doing constructions the last couple of years. All right, and part of that is because we don't really use constructions down the road, except when you take geometry in college if you're going to major in math. All right, so here, what is the circumcenter theorem? The perpendicular bisector of the sides of the triangle intersected at a point called the circumcenter that is equidistant from the vertices of a triangle. Wow. All right, so at first that seems pretty complicated, but let me show you something. All right, so here we go. All right, and again, today is just pay attention. And then once you pay attention, you don't have to write any of this out. All right, it'll become obvious to you in a minute. All right. And then hopefully you should be able to see it, all right? But please, if you miss something now from my construction, it won't be as obvious, all right? So what I'm gonna do is I'm gonna try to draw a triangle. All right, and that's a pretty good triangle because I don't want it to be equilateral or isosceles. So now, watch. What I'm going to do is I'm going to construct, well, I'm not going to construct, I'm going to draw the perpendicular bisectors of each side of the triangle. So let me see if you understand what I'm doing. So I'm going to draw the first one. All right. And I'm just going to come over here and I'm going to try to make it perpendicular to this line. But then I need to move it where? To the middle so it bisects. So I'm looking at this going, how does that look? That looks pretty good. All right, now how do I know it looks pretty good? Because that looks kind of like a what angle? That looks like a right angle. And if I'm measuring, let's see how close I am. Oh, that wasn't good. That kind of looks like that. Now if I put it over here, uh-oh. I need to move it over a little bit more. So I need to move it over about that much. All right, and let's see if that's better now. Nice thing about this iPad, that's pretty good. Now if I do it over here, still a little short. All right. Now I'm perfect. All right. So here we go. So that to me is pretty close to being the perpendicular bisector. Because that's the perpendicular bisector, please look what's going on. All right. I would like everybody to say this is congruent to this. Everybody agree with that? Mm-hmm. Now, we also know that no matter what line or what point I put here, it's going to be equidistant from the sides. All right, so now I'm going to draw the next one. All right, kind of watch now. So now I'm going to try to make it perpendicular. And then what I'm going to do is I'm going to try to find where it's congruent. How's that? That doesn't look too bad. Hopefully you kind of agree with me. We're going to eyeball that. So now I know that this right here, well, is equal to this right here. And then this is the perpendicular bisector. All right, now I'm going to draw one more. All right, and let's do this. All right, now because I've done such a great job, that's perfect. Okay, you don't have to laugh, all right? This is supposed to be congruent to this right here. Am I a little bit off? Yeah, I'm a little bit off, that's okay, but it's just a demonstration. So what I want to show you is this. All right, notice if I were to make the perpendicular bisectors, all three lines intersect in a what? In a single point. So this point right here, I want everybody to take a look at. This point right there is called a point. It's called a point of concurrency. All right, and that's just a special point now, right? That if you construct it properly, it'll always meet at one point. Now, again, obviously some of you are looking at me going, well, obviously that's not the same as that. All right, and I agree with you. All right, it's just because I'm trying to draw it. All right, now, this point right here, someone tell me what's true about this blue point. Somebody tell me, besides it's called a point of concurrency. What is it? Well, that is perfect. That is called the circumcenter. That is called the circumcenter. But why is it called the circumcenter? Watch. If I draw a circle and I pull this circle out, then it is supposed to technically touch at all, it's supposed to technically touch at all 3 points. Perfectly. So that's why it's called the circumcenter. All right, so I have just inscribed a triangle inside the circle. Now, what exactly does that mean, though? Go ahead, tell me if you got a thought. All right, well, hold on 1 second. What's true about that point? That it is what? Go. That is exactly correct. If I were to draw from here to, if I were to draw from the circumcenter to the vertex, and I would draw from here to here, and I would draw from here to there, those are all what? They're all equal. All right, so again, that's kind of something pretty cool that I always thought was kind of hard until I actually looked at it more carefully. This, and this are all equal. All right, and technically they are the what? The radii of the inscribed, well, of the circumscribed circle. So again, why does that work? All right, I'm gonna say one more time because I kind of stumbled through that. Why does that work? Everybody look up so I can show you. This blue point, I'm gonna highlight that blue point again. is on the perpendicular bisector of all three segments. Everybody agree with that? Therefore, it is equidistant from all three endpoints. That's pretty cool. Well, it's cool to me. All right, not so cool to some of you. All right, but again, so one more time. That is called the circumcenter because we circumscribed a circle around the triangle. And that blue point, the circumcenter, is equidistant from the three vertices. All right, now go, tell me your question.
So that darker line, since it should have been more over, wouldn't the three lines not intersect at one point? What if the lines still?
Well, that's because I drew it so they would intersect. I drew it so it was correct.
What happens if they don't?
It will always if you do it correctly.
Okay.
Right, now he's asking me a good question. Why is it always? So listen now, I know it's not an easy thing to understand, so that's why I'm trying, please listen carefully. I'm trying to show you that that blue dot is on, first thing I want to do is, I want everybody to look up. All right, I'm going to try to show you one thing. This was a perpendicular bisector, correct? So that means that blue dot is equidistant from here. Well, I'm going to call this A, B, C. So right now the blue dot is equidistant from A to C. You agree? Now what I'm going to do is I'm going to make it a little darker and I'm going to make it this way. Now I drew this perpendicular bisector. Now that blue dot is equidistant from B to C. Now I'm drawing this perpendicular bisector and the blue dot is equidistant from what? A to B. So now look, I know that's not the most impressive thing you've ever seen, all right? But this is just the logic behind geometry. And I tell kids all the time, to me, I don't memorize anything, right? I want you to look at that and say, that's so obvious now that I can see it. If that blue dot is equidistant from AC, and the blue dot is equidistant from BC, and the blue dot is equidistant from AB, then it must be equidistant from what? All 3 points. All right? And they just gave it a special name. They called it the what? Circumcenter. All right? And they realized that you could draw a circle, or you could inscribe the circle, or inscribe the triangle in the circle, or you could circumscribe the circle around the triangle. All right? Inscribed and circumscribed. And then we're going to show you all different little things about the triangle the next couple days. All right? But the first point of concurrency is the circumcenter, and you find the circumcenter by constructing the 3 perpendicular bisectors. All right, that is a fantastic review of today's lesson. All right, and again, I'm telling you, we're going to have 4 different things. All right, I'm going to ask you about the circumcenter. I'm going to ask you about the incenter. I'm going to ask you about the centroid. All right, and you're going to have to be able to tell me what they are. All right, and again, they're very simple if you're paying attention every day. All right. So today, perpendicular bisector, equidistant from the endpoints. All right, so now let's go back and see where we're at. All right. So here we go. Well, I'm done with the examples. I think we're good. I think you understand me. All right, so here we go. Now, I think here a lot of times what they do is they're trying to make sure you understand the words. So sometimes the pictures aren't drawn as well as they should. All right. But my question to you right now, is XZ, someone, is XZ the perpendicular bisector? Is it drawn properly? How about that?
No.
No, it's not drawn properly. Is it though? Yes. And how do we know that? Because it says it is a perpendicular right angle and it bisects YW. Come on now. That's how simple it is. Is that the perpendicular bisector? Yes. It's in the name, perpendicular bisector. It must be what? Perpendicular, and it must bisect. So that is the perpendicular bisector because YZ is congruent to ZW and XZ is perpendicular to YW. So what's the measure of XW? 7.5. And I tell kids all the time, and the test should be easy. All right, but it's not going to be easy when there's a whole bunch of different properties that you're supposed to know. All right, number 2, is that the perpendicular bisector? Yes, it is. Now, how do I know it is? That is correct. If a point is equidistant from the endpoints, it must be the perpendicular bisector. Thank you for that. Therefore, BF is what? Now, I'm trying to talk a little better in geometry for you. All right, you're supposed to be able to understand what I'm saying. Now, I've said a whole bunch. If you're going, man, these words, I'm not quite sure what you're saying, it would be better to ask now than to wait a couple days. It gets harder as we're going. Not really harder, but if you don't understand the words, it's impossible. Go. Right. Well, because this, if I was going to draw a perpendicular, I would say the perpendicular would be way over here. Right? Because, well, I'm sorry, that wasn't a very good idea. This would be the perpendicular bisector. Right? The perpendicular bisector does not have to go through the vertex. Well, because this actually is a perpendicular line, or this is a right angle. This right here is not a right angle. True? Now listen, I just said something important. The perpendicular bisector does not have to go through the vertex. The perpendicular bisector does not have to go through the vertex. That's where I think they made a mistake on this one. All right? Over here, all right, this is okay because it's an isosceles triangle. All right, so if you have an isosceles triangle, the perpendicular bisector will always go through the vertex. All right, here we go. Now, point P is the circumcenter. All right, because point P is the circumcenter, that means this right here. Everybody should draw this. What's true about this? What's true about this? And what about this right here? They are all equal. Do they have to look equal? No, because the publisher can't draw things properly, all right, for whatever reason. So all of those things are equal. What's true about ER and RK? They are congruent also. What's true about MN and NK? They are congruent. And what's true about EY and YM? They are congruent. And then we know the right angles. All right. So now hopefully someone was listening to the last question. Does this perpendicular bisector have to go through the vertex? No. Can it go through the vertex? Does it have to? No. All right, that's something important, something very important. All right, so now list any segments congruent. So what's congruent to MY? Hold up, guys. You're too fast. That is correct. EY. What's congruent to KP? MP and EP. Thank you. And what about MN? NK. And what about ER? RK. Now look, guys, I keep trying to tell, and even my Algebra 1 class, if all you're doing is writing down the information, you're not learning anything. All right. If you don't understand where those letters came from and segments came from, you need to ask. All right. This is section 1. All right. You don't want to be behind after just one section. You got to be able to tell me all that's true. And like I said, I think it's obvious. All right. So if you're not sure, it's just because I haven't shown you good enough. All right. Anybody have any issues? Yes, sir. Good for you.
Number 6, what? 1, 2, 3,
Okay, so I'm going to find ER. ER is this guy right here, right? And what do you want it to be? Not necessarily, no. Yeah, not necessarily. That's a good question, though. All right. Yeah, we're going to talk about different ways of proving that when it's true. All right. That's a good question, though. All right, so now I have the next part. All right, the angle bisector theorem. If a point is on the bisector of an angle, then it is equidistant from the sides. All right, so here we go. Watch this, guys. So I'm going to create an angle. And then what we're going to do is I'm going to try to draw the angle bisector. All right, so to me that looks like the angle bisector. Now, why is it the angle bisector? Because I'm looking at it and I'm saying that angle looks the same as that. Do I agree? All right, now I'm going to put a dot on here. All right, now I need everybody to listen because I haven't told you this. Is that the distance from that point to this side of the angle? Or is that the distance, or is that the distance, or is that the distance, or what's the distance? How do I figure out what the distance is? So they say the definition of finding a distance from a point to the line is the shortest distance. The shortest distance from the point to the line. That looks to me like the shortest distance. Now, why is that the shortest distance? Well, all lines are straight, remember? But why is that the shortest? Why is this not the distance? There you go. Whoever said that, brilliant. That's exactly correct. The shortest distance is always a perpendicular. All right, the shortest distance is always a perpendicular, so this is perpendicular to there. All right, so now I'm going to do the other one over here. All right. So that to me looks kind of perpendicular. So if that's perpendicular, then somebody can tell me what's true about this right here and this right here. What is it? They are congruent. Now you got to tell me, why are they congruent? Well, remember, this is congruent to itself. Come on. And then it would be, yeah, it is definitely CP-CTC, but you first have to tell me the triangles are congruent by what? By, well, wait a minute now. We don't know this is true yet. I don't know this is true. Angle, angle, side, right? So the triangles are now congruent by angle, angle, side. Now I'm just showing you that to make sure you can see it. Does everybody agree with me? So what is that saying? Any point that is on the angle bisector is equidistant to the sides. Everybody agree with that now? All right. And believe it or not, that is called the end center. That's called the end center. All right, which is what they're going to show you right down here. All right. So again, let's talk about it. This now, because of angle, angle, side, we know that this is congruent to that. All right. And again, That's CPCTC for those of you guys who are thinking about it. All right. So what is exactly the incenter? All right, let me see if I can draw that for you now. All right, I'm going to try to draw another triangle. I'm going to try to calculate, watch. I'm going to try to calculate now the angle bisector. All right, so if I draw this angle bisector, that looks pretty good right there. And then I'm going to draw another angle bisector here. Oh, that's not good. I'll draw this angle bisector. And what do you think is going to happen over here? It's going to go through what? Yeah. So this dot right here in the middle now is called the what? No. The incenter, that's right. Now why is it the incenter? Because look right here, guys. That's equal to that. That's equal to that. And then that's equal to that. All right, so now that green dot is equidistant. Like if I said this was A, B, C, this green dot, because it is on the pink angle bisector, is equidistant to what two sides? Wait a minute now. I said the green dot is on the pink one. I'm going to blow it up so you can see the color. It's equidistant from what? AB and BC. Now, if I said it's on this dark blue, it's equidistant from what two sides? AC and BC. And if it's on the light blue, it's equidistant from? Therefore, that dot is equidistant from what? All three sides. All right. So how does that relate? So what I'm going to do is I'm going to try to do this. I'm going to draw a circle. And now I'm going to try to do something like this so you can see. All right. Not a very good job, but close enough for me. So that point now, notice if I'm going to be a oh, come on. All right, from here to here is a perpendicular. From here to here is perpendicular. And from here to here is perpendicular. Notice that the inscribed, that's called an inscribed circle. Inscribed is how they got the word incenter. Come on now. This is the radius of the circle. It's equidistant from the sides. Notice that this is what's perpendicular. That the angle bisector, come on now, I need you to pay attention. Is the angle bisector perpendicular to the side? In other words, that wasn't very good. This pink line right here, let me go back to this pink line. Is it perpendicular to the opposite side? No. So that can't be the distance from the incenter to the side. All right, hopefully you understand what I'm just saying. Look, let me blow this up a little bit while I can. So this line down here is not the radius of the circle. That's what I'm trying to tell you. This blue line right here is not the radius of the circle. That's not what's creating the circle. What's creating the circle is the perpendicular distance from the incenter, which I'm going to call E. Let's call that E. Let's call this F, G, and H. All right. EH, EF, and EG are what is equal. Come on now. You got to listen to what I'm saying. You're going to make a mistake on the test. Everybody misses it. EA or EH, EF, and EG are what is equal. All right. It's not on the angle bisector. Yes, ma'am. The G, F, and H. Okay, so I'm happy with your explanation. Watch. See what you're hearing. All right. This point that I called the end center, that is equidistant from the sides, right? Now notice what I did. Hold on one second. I'm gonna blow this up so I can show you better. I might even put it on a different piece of paper. Come on, guys. Sorry, I'm just gonna put it on a different sheet of paper. Did I just blow that? Oh, there it goes. Sorry. Where is it at? I don't see it. Oh, okay. Thank you. It's about to go crazy. So this, I'm gonna move up here now. Oh, did I delete the page? So let me start over. That was annoying. Come on. Sorry, guys. Add a page. All right, now I can move it. All right, so now, watch me now. If I blow this up now, it should be helpful. All right, let me get rid of this garbage. Okay. All right, so here we go. So now let me try. So what I said was, and again, this is difficult, so I'm glad you asked me. This from here, from here to here is on the angle bisector. Do you agree with me? This is on the angle bisector. This is on the angle bisector. So most people think that that's the radius of the inscribed triangle, but it is not. All right, it's equidistant. In order for it to be equidistant, it has to be perpendicular. So I construct the perpendicular, and that is the radius that's created. All right, that's the distance. All right, go. Yes, if it was an equilateral triangle, you would be correct. Right? That's the annoying part. That's why I try to draw it so it wasn't equilateral or isosceles, because they have some other qualities that make it appear like that's always true. So if you draw something that's not equilateral or isosceles, you can clearly see that that is not the distance from the sides. You with me on this? All right. So again, very tricky, very tricky. And again, I'm running out of time. I still have like 10 minutes, but I wanted to make sure you guys got a visual of that. I'm not asking you to reproduce that. I'm not asking you. All right, I'm asking you to understand that and the logic behind it. All right, that's what I'm asking you to do. All right, and it's, I think personally, there's a lot in this chapter that you're gonna understand. If I just memorize everything, it's way too much. All right, there's way too much information. All right, and you start second guessing yourself if you don't understand how to construct all of these pieces. All right, so hopefully that makes better sense now. All right, so now let's go back to the notes. All right, so here we go. All right, so you see what I'm talking about on number 1 now? To me, AE doesn't look perpendicular to BA. Does that make sense to you guys? All right, but because they're telling you that EC is congruent to AE and it's perpendicular, then angle ABE has to be how many degrees? 40, has to be 43 degrees because E is on the angle bisector. All right, let's look at number 2. So YBA has to be what? Now, let me ask you this. I would have said 47 degrees and if I didn't know it. Does everybody agree with me on this? Right, so that's why I'm going to tell you, they're going to confuse you because it's going to look obvious and then all of a sudden they're going to change things up if you're not understanding. All right, then you'll think it's equal and you won't know whether it is or it isn't. All right, so is that on the angle bisector? And the answer is yes, because AY is equal to AF, and those are 90-degree angles. All right, so let's look at number 3. So what's true here? Come on, I need an equation.
2x plus 1 equals 3x.
Why? Not perpendicular bisector. Someone help him. Not perpendicular, but angle bisector. All right, even though I know what you meant. All right, it's the angle bisector because they're showing you that's equal to that. And then they picked a point and they drew a perpendicular. Therefore, those things are equal. So if we use our mad skills, x equals what? 9. So they're wanting to know what MK is, which is 19. Come on now. Remember, you're not writing that. You're telling me it's 19. Is everybody okay with it being 19? Yeah, it's very simple, guys. Very simple. All right, let's look at number 4. Is that the angle bisector? How do I know it's the angle bisector? No. Yes, you can even say that too, but I want everybody to be able to tell me it's on the angle bisector because EL is congruent to what? And they are what? They're perpendicular, all right, to the sides. So that means it's on the angle bisector, which means those two angles are now what? So that means x equals 4. Now we have to find EWL, and that would be what?
33.
33 degrees. Thank you, guys. Not bad at all. Is everybody with me? Now, again, on the test, a lot of times kids aren't even sure why it's true. It just looks true, so they make it true, right? And then you're going to miss a couple questions because you're going to think something and it's not necessarily true. So that's why I'm making sure you understand this. All right, so now, because this is the end center, because that's the end center, these are equal, these are equal, and these are equal. And what's true about UB, UM, and UP? They are congruent also. That's the radius of the inscribed circle that's not drawn. All right? That's what's true about that. As soon as they say in center, you just know it's the angle bisector, all right? And that you can inscribe a circle in that triangle. All right? So what is MU? What is MU? Yes, I want a number for MU. 5. If I said what's UB, what would it be? 5. What's measure of angle UGM? 28. What's the measure of angle PHU? PHU, 21, thank you. And HU. Ooh, who said 13? I'm super proud of you. Good job. How did you know it was 13? It's a little bit bigger than 12. What are you talking about? That's embarrassing. Oh my gosh, I was about to go, wow, I didn't realize how good I was for someone. The hypotenuse is what? 5, 12, 13. Thank you. 5, 12, 13. That's the special, the Pythagorean triples. Remember, 5, 12, 13, 3, 4, 5, 8, 15, 17, 7, 24, 25. Those are all going to be used. All right, those are all going to be used. We do not say it's a little bit bigger than 12, so I'm going to call it 13. What in the world? All right, now let's say we forgot. You would know 5 squared plus 12 squared equals c squared. 25 plus 144 equals c squared. 169 equals c squared. C is equal to 13. All right, if you weren't sure about that, or if you forgot the Pythagorean triples, all right, you know the relationship between the sides of a right triangle. A squared plus b squared equals c squared. which is, again, a little bit more than 12, so we'll go with 13. Thank you so much. All right, guys, I think that's excellent for us. All right, I don't think there's much here. Very easy. I don't think it's going to be difficult to finish up. So I want you to do both 5-1, or is it the same one? No. No, a practice and a skill practice. Do the next 2 worksheets. All right, the next 2 worksheets. Right, that's your job for tonight. Knock those out. All right, I didn't put the answers. I just feel like they're kind of easy. All right, please listen carefully. All right, make sure you get both worksheets done. All right, thank you. Today was a fantastic day. I appreciate you guys. The other 2 worksheet, scroll down and you see there's not 10 pages there. We did 2 out of.
Yes, Sam. Oh my God.
All right, my homeschool peeps. Hopefully I don't have to, tell you every detail here. All right, get them done, please. Thank you. Great.
All right, thank you.